or introduction to curve sketching. So we talked about increasing and decreasing functions, as well as finding a max or a min, which we now know is called a critical point. Are all critical points maxes or min? So if we have a critical point, automatically, does it have to be a max or a min? No, it doesn't. Okay, we saw yesterday that sometimes we have critical points where a derivative doesn't even exist. You will not have to deal with that. And sometimes critical points are not maxes or mins, they are other things happening on the graph, like a point of inflection. Okay? Today what we're going to talk about are vertical and horizontal asymptotes and how they affect our graph and how we include them in our curve sketching process. Okay? All right, so every rational function, f of x equals p at x over q at x, has a vertical, horizontal, and or slant asymptote. We know that because we have usually, not always, a place where the denominator is equal to 0. We know that that's where vertical asymptotes occur. And we will at least always have a horizontal asymptote, yes? Good. To find the vertical asymptote of a function, set the denominator equal to 0 and solve for x. Find out where that denominator equals 0. You know that that's going to be a vertical asymptote. To find the horizontal asymptote of a function, we are going to find the limits of the function as x approaches positive and negative infinity. This is new. You guys have never done this before because you've never learned limits. So now we're going to add in this extra step. It's really not a big deal. I will show you how to find the horizontal asymptote using limits. To find the slant or oblique asymptote, you have to use synthetic or long division, okay? And this will occur when you have a smaller degree in the denominator than in the numerator. That's when you have a slant asymptote. So something like x cubed over x minus 2, okay, squared, okay? So you have 1 degree lower than the denominator. Good. Remember to always ensure common factors have been divided out first, because then we know that it's not an asymptote but a whole. So if you don't divide all those factors, you're going to think it's an asymptote, but it's not. Okay? Example 1. Determine the asymptote of the following functions. Okay, first one. Where's the vertical asymptote? Very easy to see. Look at the denominator. What's the vertical asymptote?
Negative 2.
Excellent. We have a vertical asymptote at x equals negative 2. Now, for the horizontal asymptote, we're going to take the limit as x approaches infinity of your function. So how do we do this? We are going to divide by the highest power of x. So when I look at this function, I can see that my highest power of x is x to the exponent 1. So I'm going to divide every single term by x. Divide everything by that lowest power of x. So for example, everything gets divided by x. Now, what does x represent here? Well, it's the limit as x approaches positive infinity. So what we're going to look at is, if x is a really huge number, what happens to my result? What is the limit? Well, x divided by x is just, what's anything divided by itself?
1.
1. Okay. Now, if I do 1 divided by a million, what number am I going to get? Or even 1 divided by 1,000. 1 divided by a huge number. What are you going to get?
A very close to 0.
Good. You're going to get a number that's very close to 0. Say 0.000, whatever it is. But you're going to get a number that's very close to 0. And we know that with limits, we want to know what something is approaching. Yes? What is the intended height of the function? So I can now conclude that this is approaching 0. 1 divided by a huge number is very, very close to 0. So I can conclude that this approaches 0. I can also conclude that 2 over x will also approach 0. 2 divided by a huge number is also going to approach 0. So this limit just equals 1. That means I have a horizontal asymptote at y equals 1. Any questions? Yes.
Do we need to show how something in
This? Approaching 0? You must. Okay? You got it. Yep, an arrow through it, approaching 0. Beautiful. Okay. Yeah?
How does like that approaching 0 get you 1?
Well, this is 1.
Yeah.
So with my limit, I have nothing to sub in here. So what I'm left with here is the limit as x approaches infinity of 1. Well, we know that when you have a limit of a constant, it just equals that constant. 1 take away 0 is 1. 1 plus 0 is 1. 1 divided by 1 is 1.
Oh, so that's 0. Okay.
You see that?
Yeah.
Okay, over here, vertical asymptote. I take the denominator, I set it equal to 0, and I solve. So I have x squared equals 1, which means x is equal to radical 1, or square root of 1, which is just 1. Is that correct? No, why not? Plus or minus. Don't forget your plus or minus. Okay? Because we're solving here. We're solving for possible x's. So we don't know if x is a positive 1 or a negative 1. You have to include both cases. All right, so we actually have 2 vertical asymptotes here. One at 1 and one at negative 1. For the horizontal asymptote, again, we're going to take the limit as x approaches infinity of your function. What's the highest power of x in my function?
X squared.
Good. And that's what I'm going to divide everything by. Okay. And now we're going to clean it up. X over x squared is the same thing as 1 over x. Yes, when we clean it up. Here I've got 1 minus 1 over x squared. What can I conclude? 1 divided by a huge number approaches 0. 1 is just 1. And 1 divided by now a huge number squared, that's going to be even closer to 0. And so the limit as x approaches infinity is equal to 0. Okay, and I'll show this extra step. And so I didn't show it last time, and I think that's why Nathan had that question. Here, just put 0. Maybe that's more clear. Limit of a constant is just that number. So we have a horizontal asymptote of y equals 0. You guys wish you could do this again, open? And you have no room. You can screw off my other one. You go here. There. Why are we missing one? There we go. All right. C. What should I do here? I need to find the vertical and horizontal asymptotes. What should I do? Yeah, we have to factor. So before I find any asymptotes, I need to factor. So can I factor the numerator? Yes or no? Quick, quick. Can I factor? No. What about the denominator? What is it factor to?
You can't.
It's not factorable. You can't factor it. So you need to use the quadratic formula. Okay? So use the quadratic formula to factor the denominator. So using the quadratic formula, I can see that A is 3, B is -1, and C is 4. So I have x equals 1 plus or minus the square root of 1 squared minus 4 times 3 times 4 divided by 2 times A. Oops. Cleaning this up. What happens in my radical? When I clean this up, what happens in my radical?
It becomes negative.
Good, it becomes negative. You have a negative 47, I believe, all over 6. And because you have a negative, we know that there are no real roots to it. There are imaginary roots, but there are no real roots. And so therefore, we have no horizontal asymptote. Sorry, did I say horizontal? No vertical asymptote. Horizontal asymptote. We're going to take a limit as x approaches infinity of your function. What do I do next? What do I do next?
Divide everything by x squared.
Yes, highest power of x. My highest power of x here is x squared, and everything is divided by x. Okay, what can I conclude just by looking at this? Want to show an extra step? 2 plus 3 over x squared, all over 3, minus 1 over x, plus 4 over x squared. Okay, what can I conclude? Evaluate the limit. What can I conclude? Good, it's going to be 2 over 3. This approaches 0. This approaches 0. And this approaches 0. Horizontal asymptote at y equals 2 over 3. So no vertical asymptote here, but we have a horizontal asymptote. Are there any questions?
So we're expected to do the horizontal asymptote that's always.
Always. This is the proper way to do a horizontal asymptote. But you guys never learned it before because you didn't know limits. So that you did it by analysis. Look at A over, right? But, yeah. Okay, determine any asymptotes and describe the behavior of f of x on either side of the asymptote. That's what they mean by on other side of the asymptote. So f of x equals 2x plus 3 over x minus 1. We start with the vertical asymptote. Who can tell me? Do I have a vertical asymptote? If so, what is it?
X equals 1.
Yeah. There's your vertical asymptote. Horizontal asymptote, we take the limit of as x approaches infinity of your function. Okay, and I divide by the highest power of x. And I can conclude that approaches 0, that approaches 0. Anything with the denominator of x is going to approach 0 because it's divided by a huge number. That denominator is a huge number. And so I can conclude that this limit just equals 2. And so therefore, you have a horizontal asymptote at y equals 2. So here are your asymptotes. Let's put them in. So there are my asymptotes. But I need to know where my graph exists. Now for this question, we're not asking to graph. That's not what the question is asking. They want to know the behavior of f of x. How is our graph behaving on either side of this asymptote? So in a question like this, we just need to analyze. So I don't need exact points, but I need to know where my graph exists. So what you're going to do is, you're going to just sub in a random point. So you could sub in 2. You could sub in 0. If you sub in 2 and if you sub in 0, do we get positives? Do we get negatives? Where does my graph exist? Do it now. So sub in 2. Let's start there. If I do f at 2, am I here? Am I here? Oh, sorry. Am I here? Am I here?
You get 7.
Good. You get a positive number. Excellent. Come here. Again, I don't need anything more specific than that. I know the way graphs behave when you have a vertical and horizontal asymptote. They always go towards the asymptotes but never touch it, right? All right, and now when I sub in 0 or -1 or -2, you can sub in whatever you want. What do I get? A positive or a negative?
Negative.
Good, get a negative. So we're there. So now I can talk about the behavior. So, to the right of 1. So let's talk about this function as it approaches 1 from the right. So as we're approaching 1 from the right, what can I say about this function? Nothing? You can't say anything? As I approach 1 from the right, what
It
is
goes towards positive infinity.
Amazing. So, as x approaches 1 from the right, your function f of x approaches positive infinity. Your y value, right, is approaching positive infinity. Beautiful. What about as I approach from the left?
It
Now,
approaches negative infinity.
got it. Negative. Okay, let's talk about horizontal infinity. Sorry, let's talk about the horizontal asymptote. So, as x gets really big, now we want to talk about what's happening above the horizontal asymptote and below it. So above it, as x gets really big, what's happening? What's my function approaching?
2 above.
Good, excellent. It's approaching 2. It's approaching this value, 2. And it is from above, right? The horizontal asymptote. Beautiful. And we can say f of x is above the horizontal asymptote. As x approaches negative infinity, well, we can see now that f of x is below. So it's approaching 2 from below. So f of x is less than. So if you are asked a question on the test and they ask for behavior, this is what we're looking for. Okay, vertical and horizontal. And what's happening to the left and to the right, above and below.
Miss, how would you show your work if there was no graph?
I'm sorry?
How how would you show your work if there was no graph? Or can you just write the behavior?
Yeah, you can just write the behavior.
Okay.
Any questions so far? Example 3. Use intercepts, asymptotes, and the first derivative test to graph f of x. What's the first derivative test? When you say the first derivative test, what am I talking about? What's the first derivative?
Critical points.
Okay, good. So what do we do with, we find the critical points, and what do we do with them?
We draw an interval chart.
Good. We do an interval chart and we analyze. What's happening to the left? What's happening to the right? Do we have a negative slope? Do we have a positive slope? Is it a max or is it a min? Okay? Good. That's the first derivative test. Okay, so intercepts. We start there always. That's always our step 1. So, starting with intercepts. How do I find an x-intercept? How do I find an x-intercept? Oh, you let y equal 0. My denominator doesn't matter here. What I need is a numerator of 0. So what's going to make this numerator 0? Is 0. So that's giving me the point 0, comma 0. Well, because 0, comma 0 came out, what's going to happen, do you think, when I find my y-intercept? Yep, it's going to be 0, comma 0, but we have to show it anyway. So to find the y-intercept, x is equal to 0. And so I have which we already know. It already came out in the first one. Next, asymptotes. Do I have any vertical asymptotes? We set the denominator equal to 0, and we solve. Can I solve?
No.
No, you can't. I can't take the square root of a negative number. There are none. No vertical asymptotes. Horizontal asymptotes, we take the limit as x approaches infinity of our function. And we divide by the highest power of x. What's my highest power of x? Beautiful. What can I conclude from here?
0.
Yeah, good. This approaches 0, and so does this. And 0 divided by 1 is 0. So that means we have a horizontal asymptote at y equals 0. Good. Now, critical points. That's our first derivative. So what do I do? I take the first derivative, yes? Who wants to do it for me?
X squared plus 1 times 3
Keep going.
minus 3x times 2x
Beautiful.
over x squared plus 1 all squared.
Excellent. And now we clean it up. And now we factor. And we continue to factor because we have a difference of squares. Okay, why'd I do this?
Miss, I think you forgot the squared for the
I did.
denominator.
I lost it. Thank you. Did I write it above? I think I have it on the board. Yeah, thank you. Okay, now, why do we do this? Set it equal to 0, yes? And solve. So I need to know where this numerator will equal 0, right? Denominator doesn't matter. Where is the numerator equal to 0? And we can see that x equals?
-1 and 1.
Thank you. Okay, so when I sub in -1, what y value do you get?
-3/2.
Beautiful. And when I sub in +1, can I get that in unison again? What is it? Tom? Okay, so we basically have 2 points, 2 critical points. Good. Now, I want to know if these critical points are in fact maxes and mins. These are potential maxes and mins. So now I do my integral test. This is what we call the first derivative test. Remember that now. 4, 3, 4. Remember, always in order, from smallest to biggest at the top. And I write my factor. Don't forget that -3, it will affect your answer if it's not there. If it was a +3, it doesn't matter. But because it's a -3, it matters. Okay. So -3 is always going to be negative. What about x minus 1? If I talk about a number to the left of -1, so we can talk about, let's say, -2. Will the result be positive or negative? Excellent. What about x plus 1? Good. So overall, my first derivative is negative. Good. A number between -1 and 1, so let's talk 0. Then negative, positive, overall result, positive. Greater than 1, so think about 2. Overall, it's negative. So what does this tell us? Well, I've got a decreasing slope, increasing slope, decreasing slope. What can I conclude? No one knows? What can I conclude here?
-1 is a min, 1 is a max.
You got it. I've got a min here, and I've got a max. So I should have a minimum and a maximum in my graph. Now, let's graph. So start with your intercept. We have 0, 0. And then we have the point -1, -3/2, which is -1 plus 5. And then I have 1, 1.5. I have a horizontal asymptote. That can come out nice and well. Always label Always label your asymptote. There was no vertical asymptote. I know that I have a minimum at -1, so that means there's a valley. And this is a max, what you have. And then we always follow the asymptote. They're like magnets, right? We always follow the asymptote. Are there any questions? Yeah. So a vertical asymptote will never, ever, ever be crossed. The horizontal asymptotes are crossed. I know, crazy, right? Crazy.
So 0, 0 is not a 4, but not a 5.
Yeah, it is. Look, my function is going through the horizontal asymptote. I was waiting for someone to mention it. So I don't know if you guys ever saw this in NHF. Sometimes your horizontal asymptotes are crossed. Vertical asymptotes never, ever, 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 ever. Okay? So what happens sometimes with graphs is that, especially at the end, so when you're following an asymptote, sometimes it will cross very, very far away from the origin. So here it's above, but it could cross to then be below, and then it's going to follow. Yeah, so that does happen. Okay, so horizontal asymptotes can be crossed. Usually it happens at the end, far end. Okay, so let's see now how close. And we did pretty well. I went a little bit too steep. You see that? You see my hill and my valley? I made them a little bit too steep there. But with the information that we found, this is what I got, yeah? We're going to learn to be more accurate. As we add in more steps, these graphs are going to become more and more and more accurate. Okay? So let's talk about maybe how. What could have made this more accurate? Well, what you should notice here on my hill, let's look at the hill. So I'm looking at one, the maximum. Do you guys see how it's concave down? We've got some concavity, it's concave down. Does anyone understand what concave down means? Yes? Okay, good. So it's concave down between, I would say, I don't know, what do you guys think? Maybe 0 to 2.5 maybe? And then it switches to concave up, maybe even sooner than that. Where do you guys see it switching to concave up? Do you see it now switching? Do you see that? Yes? Yes. Here? No, careful. This is all concave down. That's how we have. That's how we have it. If it starts to change there, then we don't have an axe anymore. So it has to change after. Okay? Right? Because otherwise what you're going to have is this. And it's not an axe. Okay, but good. So a little bit after, we're going to find that point. That point where the concavity changes is called the inflection point. Once I find that point, I'm not putting that in my graph. My graph will be accurate. Okay? That's why I say, as we add in more steps, these graphs are going to become really good. Okay? Good. Are there any questions? Any questions? Is anybody actually here with me? Besides, I think it's Nicholas and Brian. Is that who's with me? Is it you guys, Nicholas and Brian?
Yes.
Okay.
Miss, I'm here too.
Oh, who's that? Steven?
Yep.
Hi guys, thank you for being
Yes.
here. Yeah, who's it?
Jade.
Hi Jade.
Hi, I have a question. So can you explain the concave up and concave down? I'm a bit confused.
Yeah, it's okay. We're going to actually see it in the next lesson, but I'll just say it very briefly again. So, do you understand what concave down means? Have you ever heard that word before? Maybe in science when you're talking about lenses?
Yeah.
Okay, so when you're talking about concavity, there's concave down, there's concave up. So we know that a maximum is concave down and a minimum is concave up. But there are points on the graph where it changes. So you're changing concavity. So you're moving from being concave down to concave up. Those are called inflection points, points of inflection. And we're going to find them. So once I teach you how to find them, then our graphs are going to become so accurate. So when I'm looking at this graph, Jade, I think it's happening somewhere around here. Sorry, my smartboard has to be calibrated. It's a little bit off. But I think it's happening somewhere around there, but I have a point of inflection. Okay? And I will teach you how to find it algebraically.
Wait, miss, would it also happen at 0?
Let me see, go back. It will also happen at 0. Absolutely. It will also happen at 0, and it's also going to happen here. Somewhere here. Do you guys see that? Changing again from concave up to concave down. So there should be 3 points of inflection here. Okay?
Thank you.
No problem. Okay, that's your homework for this section. So copy it down, and then we're going to do the next section. And we'll talk about those points of inflection. Is everyone caught up with the homework? How's everyone doing?
Not really.
Not really? Where are you at? Where would you
Right.
say?
I'm at 3.4.
So you haven't even started chapter 4 yet?
Yeah, but I'll start on the weekend.
Okay, good. Make sure.
Same.
Sorry? Same? Okay, just try, guys, not to fall too far behind because your tests are going to come quickly, right? Like your chapter 4 test is Friday, your chapter 3 test is Monday. Okay, so just keep that in mind. You don't want to be cramming until the end. So everyone should be, by Tuesday, so let's say after your chapter 3 test, you should be really just doing maybe 4.4, 4.5 review. Yeah? I'm going to tell you guys honestly, this one is not a problem. Chapter 4 is usually really good. It's very logical. We're learning these steps so slowly. It's not bad. You're really only learning curve sketching in one chapter. It's not bad. Chapter 5 is where the students usually have a lot of problems. Okay? And I'm going to tell you why. Chapter 5 is about taking derivatives of now more complex functions. So we're going to take the derivative of ln, we're going to take the derivative of sine, cos, and tan. It's very meticulous. So you guys lose a lot of marks on silly mistakes. So you have to be sharp. It's not a good chapter to be cramming. Okay, so don't fall behind. Okay, especially for chapter 5. Chapter 5, you need to be focused. You need to go, you need to work well, right? Because very easy to make mistakes. Okay, that's usually one of the lowest chapters. The 2 lowest chapters usually in this course, chapter 5, chapter 7. Those are usually the 2 that give the students the hardest time. Okay? And sometimes chapter 1 too, because of the limits, first time doing limits. But 5 is by far usually the worst one. Okay, so be on top of your game. Make sure you get a lot of sleep, right? Because you need to be able to catch those little tiny errors. Okay. Yeah. So December 16th is the date. What I'm not clear about, I need to find out is, I don't know if you're still here in the morning, December 16th, or if that's the first day that you're I get to see you in the afternoon. That I'm not clear about, but I know that it's December 16th. Yeah, I know, so weird, eh? But yeah, it is. Yeah, no problem. So your CPC is the last day before the break, the Friday.
Before.
Yeah. So everyone's going to be writing the CPC from home. Right? Which worked out well, kind of, because you guys are going to write the test twice in class. My other cohort is going to write 2 tests in class. Everybody writes the CPC at home. Pretty good. It worked out well.
Is there going to be multiple choice for the CBT?
Oh, yeah.
Okay.
So I hope you guys understand, like, I'm getting a lot of emails about this multiple choice. I will consider giving you guys a little bit more time for the multiple choice, 100%. But, you have to understand that this is not an ideal situation. Number one, you guys are using open books. Would you ever use open book in a grade 12 class? Let's be honest. Would you ever have open book assignments? The answer is no, you wouldn't. Number one. Number two, you're at home. You're not in front of me writing this test. You're at home writing this test. And as much as I have cameras on and whatever I'm doing, I don't know what you guys are doing, bottom line. And that's why we rely heavily on the multiple choice. It's the only way that we can keep the integrity of this course. And if you guys don't understand that, I'm sorry, but that's the way it is. And that's why the short answer is worth so little, right? Well, not so little, it's equal, but that's why we don't have more short answer and less multiple choice. It's to keep the integrity of the course, because at the end of the day, you guys are writing at home.
But Miss, if the entire class is struggling, doesn't that show?
You know what it shows me, Radim? Want to be honest? Want to know what it shows me? That you guys are not doing, I don't think you guys are doing what you would be doing if you were here. It shows me that maybe you guys aren't keeping up with the work, because the multiple choice are not even extremely challenging.
Yes, but there's no time to double check.
I understand.
So silly mistakes can be made.
And I said, I will take into consideration the time. But I want you guys to remember that if you're writing a test in class, you're writing a test that's between 36 and 43 marks. 36 and 43 marks. And you have 60 to 70 minutes to write it. You guys are taking 30 minutes multiple choice, right? And 30 minutes for a piece of paper that has 13 marks on it, where, let's be honest, the last test, the first one was just take the derivative and stop. You didn't even have to simplify it. So really, that shouldn't take 30 minutes, guys. You have to understand that. It's 3 questions. You would normally have triple that amount on a test. So it shows me that perhaps you guys are relying too much on your notes and you're not studying enough, because really, you shouldn't even have to use your notes if you're studying properly.
I mean, I don't know about the other people. I didn't even look at my notes once. Like, I didn't need to. Like,
that's good.
I still struggled on time. Like, it's not really the notes. Like, if you look at the notes, like, you'll fall behind so fast.
Yeah, absolutely. 100%.
So I don't know how much of the class even use their notes, especially for the multiple choice. Yeah. There's only like 2 minutes per question. Like,
yeah, but
it's way too hard.
Okay. In my defense, so one of the questions, actually more than one of the questions, took literally maybe 5 seconds to answer. Like, identify which one has a derivative that is not differentiable. You should be able to look at that and see it right away. We've talked about that in class many times. I very clearly showed you which function. So you should have been able to look at that one and say, oh, wait a minute, there's an absolute value here, it's that one. So yeah, maybe some of them required a little bit more than that, but many of them required a lot less than that. Work on your timing. Work on your timing.
I just think the ratio was off, because a lot of them, I think, took more than 2 minutes to do.
Radim?
That's why the class average was 71.
71, first of all, is not a bad average. First of all.
I don't know about that.
Right?
Like,
71 is actually a very healthy average. Averages of less than 70 are questionable, like 65, right? Back in the day, 65 was a healthy average. 71 is not bad. And I gave you an extra mark to boost that up, right? Which really I didn't have to, because it wasn't necessary. So I did that as a gift.
Wait, Miss, was it 71? I'm sorry.
Like, guys, this is a grade 12 university-bound course. Next year, you're going to university. And if you send your prof next year the emails that I'm getting, oh man, I would love to see the responses that you're going to get. Nobody cares. Do your work, right? Be responsible. and just get your stuff done. That's it. It's grade 12. You're not in grade 9. You're not even in grade 11. This is grade 12. Next year, you're on your own. Be responsible. Do what you need to do. Okay? I don't want to hear any complaints. I don't want to hear anybody telling me how I need to mark. I know how to mark. I've been teaching for over 20 years. I don't need your advice. I've taken into consideration that maybe you need a few more minutes on the multiple choice. Understood? Enough now. Get over it. Do what you need to do. Understood?
Okay, understood.
Okay. 4.4. So, now we're going to talk about concavity, hills and valleys, to add yet another element to our graphs. So recall, if your first derivative is greater than 0, then we know the function is increasing. If your first derivative is less than 0, then we know the function is decreasing. Similarly, we're going to look at second derivatives now. If your second derivative is greater than 0, now we're looking at the second derivative. That means that your first derivative is increasing. So let's stop and absorb that for a minute. If your first derivative is positive, your function, which is 1 degree more, is increasing. Okay? If your second derivative is positive, your first derivative, which is 1 degree more, is increasing. Does that make sense? Good. If your second derivative is less than 0, so that means negative, then your second derivative is decreasing. Okay? So what we're telling you is, when you take that derivative, it's telling you what the function before it is doing, whether it's increasing or decreasing. Okay, the one that has 1 degree more. Furthermore, if your second derivative is greater than 0, then f of x is concave up. Now be careful, we're not talking about 1 degree higher. We're talking about 2 degrees higher now. We're going back to the original. If your second derivative is positive, the derivative is increasing, the function is concave up. Okay? If your second derivative is less than 0, then your function is concave down. The first derivative is decreasing, but the function is concave down. 2 degrees up. You see that? Okay, so be careful. Don't get confused there. And we can see here that concave up is our minimum, it's a valley. Concave down is a hill, it's a mountain. As f at x transitions from a hill to a valley, there is a point where the second derivative will equal 0. That means that your function is not concave up and not concave down. This point is called a point of inflection. It's the point where we're changing concavity. Yes, I should have a glass too. You want an extra?
Not on this.
Look, there, I'm looking there. Why don't I have it? You lost it. Hold on, guys.
You can probably go.
Hold on.
Oh, it's like the box is there, that's really
You got it?
and then it's in that area, there's like, it's like this, plus there's one.
And you're right. Something happened to it. Okay. No. Give me 1 sec, I'm gonna pull it from. No, I don't think you know. There it is. Hmm. No, no. Okay, that's okay. Let's look at it from here then. For whatever reason. No, it's not. Okay, that's the thing. Let's just look at it from here. Okay, so from here, looking at this graph. So here I just have a regular polynomial function. And so let's take a look at all of our critical points. So here I have a maximum, my first critical point, that's my hill. I have a point of inflection here. I'm changing from concave up to concave down here at the red mark. That is also a critical point, specifically a point of inflection. Here I have a minimum, then I have another point of inflection so that I can get another maximum. Okay? The only way that we can transition from a minimum to a maximum or a maximum to a minimum is with a point of inflection. So again, point of inflection is where your second derivative is equal to 0, and it's where your derivative is not, your function is not concave up or concave down.
So, Miss, are POI always halfway between two critical points?
Not always exactly halfway, no. It's not always exactly halfway. It all depends on how symmetrical your graph is. Sometimes it is exactly halfway, but not always. Okay. Let me go back to my other file. Okay, determine intervals where each function is concave up, concave down, and all points of inflection. We've got to find the points of inflection, right? What should I do? What should I
And the
do?
second derivative?
Okay, good, but I can't find the second derivative until I find the first derivative.
First one.
Yep, so tell me, what's the first one?
3x squared minus 4.
There you go. And so now my second derivative is 6x. And we set it equal to 0. And we see that x equals 0. This is telling me that we have a possible point of inflection at 0. Possible. So if I sub in x for 0, what do I get for y?
0.
Good. Possible POI at 0, 0. And I say possible because we have to check it. It's the same way with your critical points. You have possible maxes or mins, but you have to test them to see if they are in fact maxes or mins. Good. Okay, so how are we going to test? We are, once again, going to use an interval test. Okay, because I want to test where it's negative and where it's positive. So I'm going to check to the left of that second derivative and to the right of that second derivative, okay, where it's equal to 0. All right, so you can very clearly see that it's negative, positive. So here it's negative, positive. Here we're concave down, here we're concave up. Because we are changing from concave down to concave up, we can conclude that this is in fact a point of inflection. So f of x is concave up when x is greater than 0 and f of x is concave down What next is lucky? POI. Okay, y equals x to the 4. So first derivative is, nice and easy, what's our first derivative? Yes.
Or x cubed.
Hold on, sorry, I have a question. Yes, what's your question? Yep.
So then at zero is actually this example, or other point in inflection, it's either concave or concavity. So right, well, either way.
It's where it's changing. It's the point where it's changing. So think of it like this. It's like a max or min. Right? It's the point, so max or min, max is the point where it's changing from increasing to decreasing. It's neither increasing nor decreasing at that value. Same here. The point of inflection is not concave up or down. It's where it's changing from one to the other. Cool? Okay, so y equals x to the 4, taking the derivative. Second derivative, 12x squared. Set it equal to 0. And we see that x equals 0 once again. So this is again a possible POI. At 0, and you sub in 0, you get 0. So we need to check. So again, we're doing an interval chart. And the interval charts are usually very simple when you're dealing with second derivatives, because by the time you get to the second derivative, it's usually not very complicated. Sometimes it can be, if it's a quotient rule, but not always. All right, so to the left of 0, am I positive or negative? Yeah, good,
Positive.
positive. I've got x squared, yes? So because I have x squared, I'm always positive. That means I'm concave up for both. So do I have a point of inflection? No. Question.
At a point of introduction, you could say that the elevation equals 0.
Say that again?
You could say like the elevation equals 0.
What equal to?
Like at that specific point 0, 0, based on the quick. Oh. Yeah. Yeah.
So 0, 0 is a point in the graph. Those are asking?
No, it's something that like, when you have like a problem with, it will give you a graph of position,
Yeah.
and then, at the POI, is acceleration zero.
Exactly. Second derivative equals to 0. Acceleration is our second derivative, right? Yeah, good. Excellent.
Wait, miss. So what actually happens there? Since it's both concave up, then why is the second derivative 0?
So you know what? I don't have the graph here, but it's going to be something like this. It's to the 4, so it's a little bit flatter. That should be second 0, 0. It's like a parabola, but it's a little bit wider and a little bit flatter at the bottom because it's a quartet. So it's always concave up.
Okay.
Yeah, I'm going to actually pull it up. Hold on. I don't know why it's on the sheet. Okay, good. I don't know why it's not on my lesson. This should be here. So this is showing our point of inflection at 0, 0. This is very similar to the graph that we drew. It's not exact. Yeah. Oh, you do? Let me see. See, I can't. The lesson's 15. Go down. I want to see which example you have. Maybe actual function is ready. Y cubed minus 4x. Okay, good to know. Y cubed minus 4x. No, x cubed minus. I have that. That's what we did. X cubed minus 5. What do you mean it's different? Think.
No, saying the graph.
Oh, it's just a new scale. Okay. All right, another one. F of x equals 1 plus 3x squared. Now, before we take this derivative, you can change this to this. You don't have to, but you can. And now it's just a simple chain rule rather than doing a quotient rule, and you're going to have so many zeros in there. Okay, so taking the first derivative, who wants to do it?
Negative 1 plus 3x squared, also the negative 2 times 6x.
Good. Okay, good, your chain rule. And now I have to take the,
The second derivative.
yeah, good. So I'm just going to do this, and I am going to do it as a quotient rule now. And now is an example where we're going to see that second derivative get a little bit tricky. So who's going to do it first? Who wants to do this derivative? Bottom times derivative of the top, minus the top times derivative of the bottom. All over, bottom squared. Who wants to do it?
1 plus 3x squared, all squared, times negative 6,
Excellent, keep going.
minus negative 6x times
Yep,
2, 1 plus 3x squared times 6x.
good, all over.
Over 1 plus 3x squared squared, all squared.
Good. Excellent. And now we need to clean this up because we're going to set it equal to 0. So let's look to factor. What can we factor out?
1 plus 3x squared
Definitely.
and negative 6.
Good, excellent. Negative 6. Beautiful. Okay, so if I factor out negative 6 and 1 plus 3x squared, I'm left with 1 plus 3x squared here. What am I left with on the other side? So I took out a 6, but I still have another, I took out the negative 6, but I still have another 6x and an x. So that's going to become good. I have a 2 here as well. And then I took that out. I took out the 1 plus 3x squared. We factored it out. So you're done. Okay, next. Clean up those square brackets. What does it clean up to in the square bracket?
Negative 9x squared plus 1.
Good, and I'm going to factor it out. What can I do next?
There's a difference of squares for 9x squared minus 1.
Good. Anything else we can do?
Cancel out.
Good. I'm going to do it both in one step, okay? Okay, what do you guys think? Are we ready? We are. So now again, guys, I only care about this numerator. What will make this numerator 0?
Plus and minus 1/3.
Beautiful. Plus or minus 1/3. So we have 3x minus 1 equals 0 and 3x plus 1 equals 0. Now go ahead and sub in those x values and let's get those actual points.
I think both y values are 3 over 4.
Yes, you're correct. Good. Okay, so these are now possible POIs. we need to check, so we need to do an interval part. Do I need to put the 6 in there?
No.
Why? It's positive, good, but if it was negative, you need it. I'm gonna leave it in just for the lesson, even though it's not needed, just to remind you that sometimes constants do have to go in. The only reason this one doesn't have to be there is because it's positive, but I'll leave it in. Okay, and then I have 3x minus 1, 3x plus 1, and I want to find out where my second derivative is positive and negative. So go ahead and do this sign chart, and you guys tell me what you get. Very good. Okay, so we know this is always positive. Okay, so help me out here. To the left of negative 1/3. So let's talk about negative 1. If I sub in negative 1, do I have a negative or a positive here? Come on, you can all do it.
Negative.
Thank you. And then next?
Also a negative.
Good. So overall, we see that we're concave up. We're positive. Okay, what about 0? If I sub in 0, what happens?
Negative. Positive.
Excellent. And so we're concave down. So now I know I have a point of inflection at negative 1/3. And over here, if I sub in 1,
Both positive.
and I have another point of inflection. So we have 2 points of inflection. So f of x is concave up when? You got it. And? Oh, I forgot my when. When x is between. Notice no equal sign here, okay guys? No. So we have 2 POIs, one at negative 1/3 and 3/4, and the other one positive 1.
Miss,
Yeah,
I have a question.
sure.
Can't POI as a point of inflection be mistaken for a point of intersection though?
Yeah, but we're in calculus, so we know POI. To be honest, POI is more used for point of inflection in higher mathematics than it is for point of intersection. Point of intersection is usually solution, just solution.
Okay, thank you, Miss.
No, no problem. I know, we use it in high school for both, and it's fine. So my graph is not showing, but I think it is on your page, correct? Do you have it on yours?
Yep.
I thought I gave you this one. So do you guys have it on yours? It looks something like this. It's following a horizontal asymptote. You've got a maximum, sorry, I apologize. And then it's following the horizontal asymptote. something like that. Okay? All right. Second derivative test for maximum minimum points. So we taught you guys, when you're solving for a maximum min, you use your first derivative test. Yeah? Well, you could, if you want, use instead a second derivative test. You're not going to use both. You're going to use one or the other. So why are there two? So this is generally how it works. If I ask you a question on a test where I only want to know maxes or min, well then you don't want to have to take a second derivative just to answer that question. So in that case, you're going to use the first derivative test. But if I ask you to curve sketch, which means you have to do all the steps, or if I ask you for concavity, as well as maxes and min, well, then you might as well just sub into your second derivative test because it's easier than doing an interval test. Is that clear? Do you guys understand what I just said? Do you need me to say it again?
Yeah, can you say it again?
Okay, so I taught you guys to find the max or min to do your first derivative test. So that's where you do your interval chart, right? And you sub to the left and the right of the first derivative to see whether you have a max or a min. But you can also check for a max or a min using your second derivative, which is what I'm going to show you now. So why are there two different tests? The first derivative test is more work. Okay, you have to do more. You've got to do the interval table. The second derivative test is very easy. However, if I ask you a question where I want to know just the max or min, I don't care about concavity, I don't want you to curve sketch, there is no reason for you to take your second derivative. It's a quotient rule. You don't want to take that second derivative. You're going to use the first derivative test. But if I give you a question where you're already taking the second derivative anyway, you might as well use your second derivative test because as you're going to see here, it's much easier. Okay? But the choice is yours. You're never going to lose marks for using the first derivative test instead of the second derivative test. Okay? You can choose whichever way you want, but you have two options. So, a max occurs if the first derivative equals 0 and the second derivative is negative. So what you would need to do is take that critical value, sub it into your second derivative and just check if it's positive or negative. So if it comes out to be negative, it's your sad face, you have a maximum. If you sub it into your second derivative and you get a positive value, then it's a minimum. It's your happy face. So let's see an example. Given f at x equals x cubed plus 3x squared minus 2, use the second derivative test to find the maximum and or minimum points. Okay, so to use the second derivative test, I need to find my derivative. So what's the first derivative? Oh, come on, guys, simple.
3x squared plus 6x.
Thank you. And now let's take second derivative. Well, actually, let's find our critical point first before I take my second derivative. So let's set it equal to 0. And if I'm setting it equal to 0, what do I need to do?
Factor.
Good. To find those critical points, right? And so I see that x equals 0, x equals negative 2. You could at this point sub these in to get your y values to find out your points, or we can do it later. It doesn't matter. So normally what you guys would do at this point is your interval chart to see if it's a max or a min. We're not going to do that. Instead, we're going to go ahead and find our second derivative. So let me just make a little note here. So therefore, critical points at 0. If I sub in 0, I notice I get negative 2. Very simple. And if I sub in negative 2, what do I get? Negative 8 plus 12 minus 2, what do you get? 2. Yeah. They can be absolute if you have something like a parabola. Of course, if they could be. But for the most part, they're your low.
So it's not like, you have to use all the steps to find out which one's the best.
Yeah. You would have to look at the end behaviors of these. Okay, so critical points here. So instead of the first derivative test, we will find the second derivative. And it's nice and easy, right? Like, look at this function, 3x squared plus 6x, that's derivative, it's easy to take the derivative of that. So what's the second derivative? And now all you have to do is take those x values, sub them in, and check if it's positive or negative. So, if I sub in 0, I get 6. That's positive. That means I'm concave up. And that means I have a minimum. And then I sub in 2. I sub negative 2 in, my other critical point, and if you sub in negative 2 now, what do you get? Negative 6. And it's negative, so that means I have a maximum. So do you guys see how it's a lot less work? Sometimes, right? Depending on what the derivative looks like. What was the point? Negative 2.
Wait, miss, what happens to those critical points that aren't max or mins? Would the second derivative equal 0? Or?
Yeah, you got it. It's going to come up, yeah, it's not going to work. It's going to equal 0 or be undefined, something weird will happen. Very good.
Thanks.
No problem. So think of it like this. A lot of times, those critical points that are not maxes or min are inflection points, and in that case, the second derivative will equal 0. If it's something like a cusp, then it's going to be undefined. Okay, and the graph is missing from here as well. I'll just do it. You guys have it on yours? Okay, good. So you can see what it is. I'll just do it roughly. It should be at 2 there, but I didn't make it as well. Okay, something like that. All right. So we see that we have our maximum at negative 2 and our minimum at 0. Okay. So second derivative test, very, very, very useful. Okay, last example, guys, and we're done. I'm getting tired now. Find the coordinates of all critical points and possible inflection points. How about you guys try this one, and then we'll pick it up. Are you guys done? Are you guys ready? Yeah. Is it the factoring that's killing you guys? Factor, do either factor theorem or factor by looping. Looping will be probably faster. You guys do that? It's too early in the morning. Here, let's do it. Okay, so let's do it. So find the coordinates of all critical points and possible inflection points. That means we need a first derivative and we need a second derivative. So let's go ahead and find the first derivative, which you guys must have already done by now. What is it? Beautiful. Excellent. Now, from here we need to factor. So you can do the factor theorem, or you can use factoring by looping. I know that you guys find factoring by grouping challenging, and so I'm going to do it that way. Just or it's not that you guys find it challenging, but maybe you don't always look for it, right? You don't think of it as one of your options. Okay, so if I do factoring by grouping, what I'm going to do is I'm going to take an x squared out of my first two, and then I'm going to take my 9 out of my, or negative 9, to give me that common factor. And then I factor again, right? My GCF is x minus 3, and then it's a difference of squares. There you go. Fully factored. So if you were doing the factor theorem, then you guys will remember. Yeah, you can use synthetic division. So what you can do is you look for a number that when you sub it in gives you 0. So in this case, the two numbers that would have worked would have been negative 3 and 3. And a good way to find your factors is to look at your first term coefficient, your last term, and then because you know it's got to work for A over B, right? It was a fraction of those two, right? Okay, so you always try, when I do factor theorem, I always start with plus minus 1, and then I would jump in this case, plus minus 3, right? Because that's not 25. Okay, good. From here, now I need to set this equal to 0 to get my critical point. Well, I've already done. And so now my critical points are negative 3 and 3. So negative 3 comma what? You can give it to me as a decimal. And 3 comma what? You can give it to me as a decimal. The reason I say you can give it to me as a decimal is because we are graphing. And so you're getting to our, or when we are graphing, predicting we are. And so decimal digits.
For -3, it's -74.25.
Sounds good. And over here, 3 it's?
33.75.
Yeah. Thanks, gentlemen. Okay, so now we're going to find our second derivative. I'm not going to use my first derivative chart. I'm going to go ahead and find my second derivative, and I can always sub into the second derivative if I want to know if they're matched with something. Okay, so second derivative is? I can't see it, so hold on. Yeah, 3x squared. Yeah. Yeah, perfect. And then we set it equal to 0. And of course, we must factor. So take out your 3. Always common factor first. And then, can you use product and sum here? Or crisscross, whatever you use.
X minus 3 and x plus 1.
Good. And so, we have possible inflection points. At 3 comma, sub in, oh, I think we already did that one, 33.75, and sub in -1. What do we get?
-30.25.
Good. So do you see here, this is an example where the critical point most likely is going to come out to be a point of inflection. Now the question doesn't ask us to find out whether it's a max or min, so I don't have to, and it doesn't ask me to confirm that they are POIs either. It just asks for possible points of inflection. However, if I wanted to know whether those critical points are maxes or mins. I have my second derivative. All I would have to do is sub in -3. Is it positive or negative? If it's positive, it's a minimum. If it's negative, it's a maximum. Then I sub in 3. If it's positive, it's a minimum. If it's negative, it's a maximum. If it's 0, it's not, it's a plane effect. Right? No, second derivative is equal to 0. It's not a plane of reflection. You get 0, it's neither positive nor negative, and so it can't be a max line in. Are there any questions? You guys feel good about this?
Yes.
It's okay.
Zero. Why is it still a critical point?
Why is what still a critical point?
If I test max and mins,
Yeah,
if the answer is 0, why is it still a critical point?
critical points are not just maxes or mins. Critical points are special points on your graph. They're critical points that occur on your graph. So sometimes they're not maxes or mins. Sometimes they are, in fact, points of inflections, cusps, other things like this.
Okay, I see.
Yeah.
Thank you.
Yeah, no problem.
Miss, can I ask some questions from chapter 3?
For sure you can. So you guys are good here? Is everyone good here? Okay, so this is the homework for this section. Another mistake, number 8, the first part B. Y value of POI is incorrect. Okay, so it should be plus or minus 10 root 2 over 9. So number 8, I. Or 1. However you want to do that. Okay, so who was it that had questions?
I had a question on 3.3. Well, I can just tell you the question. It just gives you the dimensions of a rectangle with an area of 64 meters squares.